a lot, Guillaume. Also thanks to McDonald Institute for the invitation. As he said, we are going to speak about, I'm going to speak about the application of this technique I work with, Accelerator Mass Spectrometry, to the radioassay for rare search experiments in Astroparticle Physics. So, why is so important the radio purity in this experiment? So, as you know, there are two important kind of experiments right now. One are the neutrinoless double beta decay, in which we are looking for the signal that this decay would produce in this peak that would be just in the energy of the Q value of that decay. And because of that, since we are looking for something with a very high half-life, we need to have radio pure and no background. And the background will be problematic when we have particles gamma or beta in that region. The other kind is direct dark matter detection, where we are looking for these nuclear recoils produced by the scattering of these dark matter particles with the detector medium. In this case, the most important backgrounds would be the neutrons would be interacting the same way as the dark matter, and the nuclear recoils that are produced for alpha decays, but also we can have other sorts of background. So one way to reduce the background is to build this detector underground to shield, to use the Earth shield to get rid of the cosmic rays. But in any case, you still have the problem of the natural radionuclides that you still have to in the materials that you are using to build the detector. So you have to do this selection of materials in order to reduce this to the minimum. It's especially important when we're speaking about decay chains, because for each decay of the parent radionuclide, you are going to have a lot of decay particles from all the daughters also. So two important radionuclides in this case are uranium-238 and thorium-232, because they are natural occurring isotopes because they are primordial radionuclides. And it's important to know that in these decay chains, it happens that when enough time had happened, then all the production and the decay of the daughter radionuclides can have this equilibrium. So they have this thing called secular equilibrium, where all the daughter radionuclides should have the same activity as the parent radionuclide. But this is not always the case, because, for example, in the case of uranium-238 change, we have in between, during the chain, this radon-222 that is a noble gas, as has a half-life long enough to be able to escape the solid material where uranium is, and then decays after some days. So the daughters of radon are played out until they are achieve this lead-210 radionuclide, which is also very important because then the half-life is relatively long, and it forms its own decay change with bismuth and polonium-210. Also, then for this radioassay, we have different techniques that are typically used. They can be separated in two main groups. One is the radiometric, where we are measuring or the decay from the radionuclide we are looking for, gamma or alpha counting typically, or also to look for the decay of radionuclides produced after activating the sample in a nuclear reactor. This is the neutron activation analysis. When half-lives are too long, then because of the indirect relationship between activity and half-life, it's better to use mass spectrometry, where we are measuring directly the ions from the isotope of interest. So, accelerator mass spectrometry is in this last group, but it has not been typically used for radioassay. The main difference, well, first I want to say, AMS was developed in the late 70s to solve the problem that during radiocarbon dating, there were a lot of samples that could be used for radiocarbon dating but cannot be measured by radiometric techniques. Just explaining a little fast, radiocarbon is produced in the atmosphere from the interaction with cosmic rays. So the CO2 has a higher amount of C14 than, for example, the crust, the Earth crust. So So then, since it's in the CO2, it's getting incorporated in the food chain, starting with the plants. So all the living beings have in their tissues, in their active tissues, this ratio of C14 to the stable C12. And when a tissue becomes non-active or a living being is dead, then it starts to decay. So knowing the ratio, you can know how much time the tissue was not active. The main problem it was that they needed always to find a huge mass of sample in order to be able to measure this radionuclide with a very long half-life of 5,000 years. So since it's so typical, for example, in archaeological sites to find just little pieces of bone where you can use just milligrams of carbon, then you would need or high masses or long times of measuring. Also, this could not be measured by conventional mass spectrometry techniques like ICP-MS because the background, the molecular background from the stable isotopes of carbon with hydrogen would be much higher than the ratio that you want to measure. So even reducing the ratio 6 order of magnitude, this molecular background, with the different techniques that are used to reduce this background, you still have a much higher background from this than if you than the one you want to measure. So in the late 70s, they realized that they could use tandem accelerators to solve this problem. And they developed this technique that is AMS, I work with. So how works AMS? First, you had to prepare the sample chemically to a final form that will depend on the radionuclide you want to measure. For radiocarbon is graphite. So then you do a negative ionization by sputtering with cesium ions of this, so you create a negative ion beam. This is already a good thing for us because it's gonna get rid, in some cases, of the stable isobars that these radionuclides typically have. In the case of carbon, this stable isobar would be nitrogen-14. Since nitrogen has a negative electron affinity, you are not producing any negative ion or nitrogen, so you are not going to have any background from nitrogen. Then you do a first separation, typically at least with a magnetic dipole, which is selecting the ion that you want in this low energy sector. That has to have a very good resolution. Typically this magnet has a resolution to be able to solve perfectly one atomic mass unit even for elements like uranium or plutonium that have a very high mass. Then the tandem accelerator, first, the positive potential of millions of volts attracts these negative ions to the center or terminal. So we have a first acceleration. In the center, we have a gaseous or solid material that is called the stripper, which strips the electrons from these ions, and therefore is also not only converting the charge from negative to positive, but also destroying the molecular ions. This is the most important thing for AMS because that's the reason we don't have any molecular background in AMS. Then these positive ions are going to be rejected, so we have another acceleration. And then with another magnet, we do another separation of masses. We typically measure the stable radionuclide with a Faraday cap because we have currents of microamps or nanoamps, while the red nuclide that has like 1 trillion times lower than the stable isotope has to go to an electrostatic analyzer like this to have a better resolution, and then measure by a particle detector that the most used are gas ionization chambers because the high efficiency of almost 100%, and because they have a very good resolution for the energy, which is pretty important for AMS because all the ions with the same mass charge ratio as the one you want to measure are going to arrive. So you want to separate the energy. Also, these gas ionization chambers, you can separate the anode, for example, in 2 or several anodes. So here, for example, we can see an example in the bibliography of how this different ionization in the medium. Here we have, for example, for this case, the energy deposited in the first anode and the energy deposited in the second anode by different ions. So when we are measuring, for example, beryllium-10, both have the same energy, but since they have a different atomic number, the boron is gonna leave more energy in the first anode and less in the second. So you can do this separation of the ions of beryllium, of boron. So you get rid, in some cases, also of this potential background of the stable isotope. As I said, we had to prepare the samples, and it's important to know that typically the final form depends on the radionuclide you want to use, and depending on what's the final form, you have to mix it with some conductor material or not. In order to produce ions by cesium sputtering, we need a conductor. So, for example, with graphite, it's not a problem, but when we are measuring aluminum-26, then we are using aluminum oxide, so we had to mix it with some copper or with some silver to be able to produce the ion beam. Also, beside the samples we want to measure, we had to measure blank samples, these samples that don't have the radionuclide of interest, because we always are going to have background from contamination in the lab, from some processes that happen in the machine, and also some standards, because since it's different how you're measuring one isotope and the other, there are some losses for the radioactive isotope that you had to correct. Also, you can do two different approaches for AMS measurements. For some samples, you are interested in measuring the ratio. You typically have the stable isotope of the element in that material. So you want to measure the isotopic ratio of the radionuclide to its stable isotope. So in this case, you don't require in any step of the chemical preparation 100% chemical efficiency, because any loss in the radionuclide is going to be the same in the stable isotope, because that's only depend on the element. Also, it's better that you maximize all these efficiencies, because then you are going to need to destroy less amount of sample for the same final material that you need. Also, you can do sometimes measurements in some materials where you don't have the stable isotope. For example, when you are measuring aluminum-26 formed in silica by cosmic rays, you don't have the natural aluminum. So in this case, you have to be sure that at least the first step is a total dissolution of the sample. So when you add the natural isotope of the element, then you know that the final ratio that you're gonna measure in the machine can be related to an initial concentration in the sample itself. Right now, AMS is used for a huge variety of radionuclides, cosmogenic and anthropogenic, with high half-lives, but always with, if you are able to deal at least with the stable isobar, which is the main problem, the main challenge of any new AMS radionuclide. Also, it's used to much more applications of C14 dating. So C14 is also used to control the amount of CO2 that comes from fossil fuel burning and not from natural sources, because this fossil fuel has no C14. Also, some cosmogenic radionuclides are used to date geological material or meteorite. Also, some anthropogenic are used in the characterization of waste or as tracers in water currents. And also, C14 and calcium-41 are used as tracers in some metabolism studies to trace metabolism changes. So, our application is something that has not been used so much in AMS. It's the application of this to the study of the purity of the material that we want to use for these rare event searches. In comparison to radiometric techniques, we don't have the problem that the relationship of the sensitivity is related to the half-life, so it's better for long-lived radionuclides. While in comparison with mass spectrometry, the main advantage is that we are sure that we are totally destroying the molecular background. All our measurements are being performed in the André E Lalonde AMS Laboratory, which is in the University of Ottawa, in the main campus of the University of Ottawa. It's the only operating AMS facility in Canada, so it's pretty convenient for us in Carleton to have this facility in the same city. It's a pretty new laboratory, so the design is very good, and they have fully equipped laboratories for the different radionuclides. But the team, even when it's a new lab, the team is of experts who was in Toronto. So they have a lot of experience in the AMS, and they are already doing a lot of routine measurements. So we are studying right now 2 branches of the project. One is the measurements of uranium-232 and thorium-238, and thorium-232 concentrations. The main difference of these radionuclides with common AMS radionuclides is that they are primordial. They are not cosmogenic or anthropogenic. So we are going to have these radionuclides in any solid material, so we want to avoid any chemical preparation to avoid this contamination. So what we are doing, we want to try is to measure by directly sputtering the sample we want to measure with no chemical preparation at all. The main problem is that then we cannot add an isotope of reference to measure these isotopic ratios, and we need another way to calibrate our measurements. And that's where we are working on. For lead-210, this is more close to another AMS radionuclide, because we can do chemical preparation. We would add the stable lead to measure these lead ratios. And the main concern for these rare event searches studies is this alpha decay from polonium that would lead to alpha N reactions, and the method would be a huge problem. Then we have this chemical preparation to the lead fluoride sample, and I will explain much more later about this. So in the case of uranium and thorium, the techniques more used for this in rare earth searches experiments are ICP-MS. ICP-MS is also a mass spectrometry technique, which also use low mass of sample as AMS. But in comparison to what we want to do, we have this chemical preparation that we know that for uranium and thorium, it's always giving a little. And even when the molecular background for uranium and thorium is much lower than for other radionuclides, which have a stable isotope, it's still there. And even with techniques that can reduce a lot this molecular background, you can have some of these, depending on the material, even more or less. So in AMS, we wouldn't have these 2 problems. If we can measure by directly sputtering, it would be no chemical contamination, and we will have total molecular destruction. The other is neutron activation analysis, where samples are activated in a nuclear reactor. The main problem of this is that these reactors are typically not so accessible. It's a problem that sometimes AMS has, but in this case it's worse, that there is much less kind of these reactors that can be used for this than AMS facilities. So, as I said, the idea would be to sputter directly the sample. The first sample we are working with is copper. So the idea after sputtering the sample would be to select these ionic clusters of thorium and uranium with copper to be sure that all the uranium and thorium that we are detecting afterwards in the detector is coming from the copper material itself. Anyway, just in case, we also did this redesign of the targets. These are the targets that they use typically in the U Ottawa facility. You typically press a powder here, but then you're gonna sputter the powder and also a little the target where you are pressing the material. So that's not a problem for other cases, but for us that would introduce a contamination, because this is gonna have also uranium-232 and thorium-238 and thorium-232. So what we did is this redesign where we cut the upper layer and we do these slits, so we can introduce the copper target inside. So we can use, see here, a unused target where we can see that the huge part where it is sputtered is concentrated in the material, but also this halo of places where there was no so much sputtering is also in the copper. So we know that everything that is coming from the target is coming from the copper. So the problem we have, we check that we can totally detect the uranium-238 and thorium-232 ions with that. The problem is how we calibrate these measurements. So the idea we had is to form these other reference materials, so measure also these standards, where instead of uranium-232 and 238, and thorium-232, we would add these non-naturally occurring isotopes of uranium and thorium, 233 and 229, and have this copper with the known amount. So whatever is happening with uranium-233, we know that it should be the same as uranium-238 and the same for thorium. The main challenge is that we have to ensure that the material that we are producing is totally homogeneous and the concentration is known and also homogeneous. So when we are sputtering, we know that it's happening the same as with uranium-238. So the first challenge that we have for that is, okay, then well, we have to produce this ferrite powder, but since we need something similar to what we are going to measure, we need to turn this powder into a solid material. So the idea would be, after having this powder spiked with uranium-233 and thorium-229, applying this sintering, that is applying pressure and temperatures close to the melting point of copper, but without achieving it, so it becomes solid. I designed this device, this sintering device, where you can press the copper and you put it in this muffled furnace for 6 hours, and afterwards this ultrafine powder of less than 100 micrometers turn into this piece, where you can get this more little piece that you can actually insert in the target, of course, after polishing of this, etc. And here you don't care so much about the contamination, because you are going to measure something that is not naturally in the target. So the first procedure I tried, it was just adding 1 milliliter of uranium-233 solution, because we still didn't have the thorium-229 sample. Just drying this little drop, which is already in the copper powder, do a very repeating mechanical mixing, and then performing the sintering. So when we did the test together with this ultra clean copper, the Aurobisk copper, we checked in the machine that even when these samples, because of all the process, they get super contaminated, they had huge rates of uranium-238 and thorium-232, the ultra clean copper was not giving these high rates. This means that when we are changing from sample to sample, there is no this cross-contamination that would be a problem for us. So we know that we can do very clean measurements. The main problem is that we didn't detect the uranium-233, or so maybe the homogenization didn't work, which is what I'm pretty sure it happened, but also it could be that the uranium-233 got lost in the process of sintering. So we had to look for an alternative for that. So one of the possibilities is trying to dilute this 1 milliliter of solution all over with several milliliters of water until it's wetting all the copper. The main problem that I see with this is that I think it's going to go to the bottom, all the solution in the end, and all the uranium and thorium is going to concentrate in the bottom. So another possibility I want to look for is to do this coprecipitation of copper with uranium and thorium, where we would have a solution of copper ions, of a copper salt, then add the spikes of uranium-233 and thorium-229, and then do a hydroxide precipitation of copper. Then the uranium and thorium would precipitate also like hydroxide, and then this hydroxide can turn into oxide just by heating it, because it decomposes, and then reduce it with hydrogen. And we know that they have a system for that in André E, Ottawa. So it would be reduced to the metallic copper that we need. Another possibility that is not relying on having reference material would be doing a little of chemistry to the sample, but not using any solid reagent. So what we would do is to dissolve a tiny part of the sample we want to measure, then in ultra clean nitric acid, then we would add the uranium-233 and the thorium-229 and electroplate the copper again in an AMS target. With this, the advantage is that we would be measuring these isotopic ratios that can be totally directly related to the initial concentration. And we don't care anymore about the different efficiencies for copper and uranium and thorium, because any different efficiency for uranium-238 is going to be the same efficiency for uranium-233 and the same for thorium isotopes. So for lead-210, they had worked already a little in the AMS group at U Ottawa. The techniques that are typically used before using AMS for this, for relevant searches, are the gamma counting of the lead-210 decay itself. The main problem of that is that it's a very low gamma ray, so there is a problem of efficiency for that kind of energy in the detectors, and also the calibration is typically problematic at those energy. These techniques, even when they are using underground detectors, they need huge masses of at least several hundreds of grams and long counting times. The other possibility is to assume that we have a secular equilibrium of polonium-210 with lead-210. So if you are measuring the activity of polonium-210, that should be the same as lead-210. In any case, polonium-210 is the one we are worried about, because it's the one that is going to produce these alpha N reactions in the detectors. But the main problem of this is that if you don't know whether this lead-210 that is producing polonium-210 was deposited or plated out, then you can have that the polonium-210 is this low and the lead-210 is this high, and then the polonium-210 is going to start to create. So in order to study the long-term activity of polonium-210, it's more important to measure lead-210 and not polonium. So the measurements of lead-210 would be done, as I said, producing lead fluoride targets, and in this case we would select this kind of ion. And as a matter of fact, the good thing that has lead is I'm going to show you this thing of how good these magnets are used, where we can see that the low energy magnet can separate perfectly the different stable isotopes of lead, even when they are with a plus of 57 atomic masses. So they are huge molecular ions, but even with that, we can totally separate them with the magnet. So the main challenge we had when we were studying this is that for the precipitation of lead fluoride, when you are coming from an acid solution of lead, then the acid solution means that you have a lot of free protons in the solutions. So when you try to add the hydrofluoric acid that you need to produce the lead fluoride, then in this equilibrium of the HF wants to go to the part where you don't have dissociation, so you don't have fluorides, because when you have a lot of one side of the equilibrium tends to go to the other side, and therefore if you don't have fluorides, you are not producing lead fluoride. So we solved this by adding another step before, that is a precipitation of lead hydroxide, which precipitates when you add ammonia until basic pH. So then first you do this precipitation. When you get rid of the solution, you have just the solid precipitate of lead hydroxide. With that, you just add HF. So the only acid in the medium is the HF itself. Therefore, you have the fluorides, and after 1 day, you have the fine precipitate of lead fluoride. We also checked with the first measurements that we have a limit of detection of the ratio that we are measuring, lead-210 to lead-206, in the order of 10 to minus 14, that is close to what we measure for other radionuclides in AMS. So taking into account that we had to add an amount of 10 milligrams of natural lead, this means that our limit of detection is 100 microbecquerels. This is going to depend a lot then in terms of specific activity on the amount of samples that we can treat, depending on which kind of sample we are using. Maybe for some samples, here you can say the sample mass that we could use, and how is that related to the limit of detection for lead-210. If we can use only less than 1 gram of sample, between 0.1 and 1, then we will be more in the hundreds of millibecquerels per kilogram. When we are able to dissolve more sample and separate it from the lead that we are adding, then we would improve this limit of detection to several tens of millibecquerels per kilogram. With the first samples we have worked with for lead-210 are this lead-free solder. This was done because it was measured also already by the University of Alabama group at the Survey facility, an underground facility by gamma counting in South Dakota. So in order to compare our results with them, and also this Kapton ultra-thin polymer, that is a polymer that is typically used for the printing of electronic circuits in the detectors. We developed the chemical methods for these two kinds of sample. In the case of lead-free solder, this is almost 100% tin. So the tin is dissolved in aqua regia, that is a mix of nitrogen and hydrochloric acid. Then we had to do several precipitations at different pH, so we can separate most of the tin that we have there from the lead that we are adding from the carrier. And then finally we have the lead hydroxide precipitate that when we do make react with the HF, then the little tin that is still there is going to stay in the solution in the HF while the lead is precipitating as lead fluoride. So we had this final separation. In the case of Kapton, Kapton is a very resistant material chemically. So we had to go to a microwave digestion system where we are digesting in nitric acid at pretty high temperatures at 230 degrees. With that, we totally dissolve the Kapton already with the lead carrier. We observed also that when we are coming from concentrated acid, the final precipitation of hydroxide is not happening or happen very little. We don't know why, but we don't care. So what we did is just add this step where we evaporate into dryness the sample and then redissolve the solid in dilute acid, and then we have a proper precipitation of the hydroxide and then the formation of lead fluoride that we need. We did these measurements in August last year. So here for the lead-free solder, in the first we have the results from the group of University of Alabama by gamma counting at Surf, and these two are the measurements of two different aliquots of our measurements. We see that our results are in the same order of magnitudes as theirs, but there is some difference. But our collaborators in the University of Alabama, they told us that because of this problem of calibration I spoke about, of the efficiency of the detector, they are not sure if they should add much more uncertainty to that measurement. So they trust more our results than theirs, because they still have some problems of calibration with that detector. In the case of Kapton, all our samples we gave 0 ratio during the measurement, which means that this was below our limit of detection. The problem is that because of some problems we had during those measurements with the samples and with the machine that are solved already, the background was 1 order of magnitude higher than the one, for example, we had before. So in this case, since we were using also a sample mass of 0.15 grams, we had this upper limit for the lead-210 concentration, that is 40 becquerels per kilogram. So what I wanted to do was to improve this level of detection. We know that we can improve this. We that already knew because we were measuring before limit of detection of 10 to minus 14. But other thing that I said, it's okay, another thing we can do to improve this sensitivity in terms of specific activity is to increase the mass sample 1 order of magnitude also. The only challenge is that in the microwave digestion system, you cannot digest more than half a gram of organic material per digestion. So you have to separate in 4 different digestion for each sample. So do 4 different aliquots with 1/4 of the carrier. And in the end, mix all the solutions in one and continue with all the procedure. And we see in the end that we have the same hydroxide and more or less the same hydroxide, lead hydroxide amount that we had when we were using 0.15 grams of Kapton. So we are still separating all the things that are in the Kapton from the lead. These measurements are pretty new from the last week, are from these new Kapton samples, where we already have a more close blank sample, a blank number, as we had in the previous measurements. And taking into account that we are using a much higher amount of sample, we reduce this limit, this upper limit of the lead-210 concentration to orders of magnitude. With this order of magnitude, well, taking into account that this Kapton was also measured its uranium concentration by the ICP-MS group at PNNL, they measure a specific activity of uranium-238 of 10 millibecquerels per kilogram. So if we assume that the Kapton, the lead-210, sorry, is in secular equilibrium with its parent uranium-238, then we know that the Kapton should have this 10 millibecquerels per kilogram. If we don't have that secular equilibrium, then we know that the activity has to be higher. So at least, and now we know that this lead-210 concentration should be between this or this level. So at least we are giving now a range between 10 and 490 millibecquerels per kilogram for this sample. In order to compare this with the surface, with the activity per unit of surface, which is the important thing of Kapton, because you typically have this circuit and you need this surface of Kapton, you don't care depending on the thickness. So that, applying that, we were measuring this 25 microns thick Kapton, we would have a limit of 18 millibecquerels per square meter, that in order to know how much is this is what you can plate out in high density polyethylene in the radon concentration of a snow lab during 7 days. If this plating out of lead-210 is not pretty known in Kapton, so if it's higher than for polyethylene, then it's the concentration that you can plate out in a snow lab for just 1-2 days maybe, or if it's lower then it would be higher, but you have to take that into account. So the last thing I want to speak about is about the possibility of using AMS radionuclides, which are already a typical radionuclides measured by AMS, but applying that to this radioassay. So, for example, the most iconic AMS radionuclide, radiocarbon, this is typically not a problem in neutrinoless double beta decay, because it's only produce a beta particle of maximum energy of 150 kiloelectron volts. But it could be a problem in direct dark matter detection. The problem is that it's assumed a lot of times that all the polymers that you're using, all the polymers are coming from crude oil. So crude oil is a fossil, it has no C14, so in this case it wouldn't be a problem. But it's known already, like there is this paper in the bibliography where they measured these radiocarbon ratios in different materials like acetone, ethanol that are typically used, and for example THF, which is used for the polymerization sometimes. And they measure a ratio only 10 times lower to the one in biological material. So in this case, we would have some concentration of C14. So if you are assuming that node is much lower, but you don't know the origin of these polymers, then you are doing a wrong assumption. So if you know that the polymer, of course, is coming from crude oil, then you don't have to do any measurement. But if you don't know the origin of the polymer, that is typically the case with companies, they don't tell anything, then you have to be sure that the C14, C12 ratio is below the background of lead-210 of AMS, sorry, that is 10 to minus 16, 10 to minus 15. But if you can have 10 to 15, you have to know it. Another possibility is also to measure these other typical cosmogenical radionuclides that are in some materials. Like again, if you are sure that the company that is providing, for example, the silica, is getting this, the base material from underground parts, then you know that it's not going. It hasn't been exposure to cosmic rays, So you shouldn't have, for example, aluminum-26 or beryllium-10. But if you don't know if it could be from surface material, then it's known that beryllium-10 and aluminum-26 are produced in silica when it's a surface material for several thousands or millions of years. So if you don't know the origin of material, it would be important to do the radioassay of this kind of long-lived, very long-lived radionuclides. So concluding my talk, I'm sure that there can be a strong symbiosis between the AMS facility and the community and the Astroparticle Physics one, because we can help to do better radioassay, but also the AMS community can get a lot of new techniques and develop new things that can improve a lot the technique itself. For the measurement of uranium and thorium, we see that it's fine. We can do these measurements, new AMS measurements, by directly sputtering the samples, but we still have to solve the problem of the calibration of the measurements. We have proved that we have an excellent limit of detection of lead-210 for lead-210, so it's pretty useful when we have just grams of sample available. For example, for Kapton, if you want to have hundreds of grams, you have to purchase a lot of Kapton, because something like this of Kapton is just 3 grams because of the thickness, and also that we should totally study the application of common AMS radionuclides to the radioassay. Thanks a lot.